All right, let's get going with our second week of astronomy. So starting with our own solar system, we're going to talk about the difference between heliocentric and geocentric. So the first model that scientists thought explained why we have night and day was this geocentric model. So that word part geo means earth, so meaning earth is at the center. So Aristotle and Ptolemy thought that earth was at the center and everything revolved around the earth. And that's how they explained why we had night and day. It wasn't until much later that Copernicus introduced the sun-centered model. So that word helio means sun, and that the sun is at the center of our universe. And they adopted this model over the geocentric model because it explained all of the motions of the planets. So when the telescope was invented and we were able to see other things in the universe and how they were moving, especially in our own solar system, they adopted the heliocentric model, meaning the Earth is at the center and all the planets in our solar system revolve around our sun. So you can see in this picture, this is a list of the planets in our solar system, starting from the Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. My very eager mother just served us nachos, and that's how you can remember the order. But it explained again that the Sun was at the center and all of these planets revolve in an orbit, elliptical shaped orbit around our Sun. So let's talk about our Sun. Here you can see the different layers starting from the inside of the Sun and working our way out. We have the core. That is very important for you to know that the core is where fusion happens. That's where energy is produced. And then we have the radiative zone because that's where fusion is occurring. So we have radiation release there. And then followed by the connective zone, the photosphere, which is the layer that's thick enough for us to see from Earth. So when we're looking and we see the Sun, it looks solid. It's not because it's solid, it's just that's where the gas is dense enough that we see it. So that's the photosphere. And then this is the chromosphere. And then, of course, we have the corona, which is the light that's coming off the Sun. So if you look over on the left, it's a large ball of gas made mostly of hydrogen and helium held together by gravity, and that hydrogen and helium piece is really important because that's what occurs in fusion. Those hydrogen atoms, 4 of them, are fusing together to create helium, and a lot of energy is released from that fusion piece. The other part you need to know is that the Sun is so large, it contains 99.9% of the mass of our own solar system. Okay? So the Sun is the first, so start making our way out. The first 4 planets in our solar system are called terrestrial planets. They are Mercury, Venus, Earth, Mars, my very eager mother. And they share similar characteristics. Those characteristics is that they are located in the inner solar system, the first 4 planets. They are solid surface of rock or metal, meaning they have a high density. And we talked about that in our lab the other day, that those gases were burned off. They rotate slowly. They all have a weak magnetic field. There are few moons. And I keep going back. Hold on one second. And there are no rings on the terrestrial planet. So make sure you get all of those characteristics written down. The next set of planets are called Jovian planets or gas giants. Those are the outer 4 planets, Jupiter, Saturn, Uranus, and Neptune. They are our outer solar system. They're far from the Sun. They don't have a solid surface. They are primarily gaseous, which is why they are so large. So they have a low density because they're made of mostly gas, and a low mass. They rotate fast. They have a strong magnetic field, and they have many moons and many rings. So we know Saturn is known for its rings, but actually all of the gas giants have rings. Saturn's is just more visible to us because it's made of large ice chunks, so we can see them really well. Okay, so those are the Jovian planets, and we can remember the order of, we're going to go to planet characteristics first. So these are the things you need to know about each planet. So make sure you get all of these written down. Mercury is closest to the sun. It's very hot and dead and barren. It is similar to our moon. That is important for you to know, that it is similar to our own moon. And maybe I can stop going forward. Okay, similar to our moon. Venus is a similar size and density to Earth, so we call it Earth's hot little sister because it is just like Earth in size and density, but it is extremely hot. There's a large amount of carbon dioxide on the surface, and because of that, carbon dioxide is a greenhouse gas. You guys learned about that previously. Because there's so many greenhouse gases, Venus just continues to get hotter and hotter because that heat that comes in is trapped on the surface and it does not get released from Venus's atmosphere. It just stays there. So the temperatures continue to rise. Heat comes in, there's no light. And the other thing that you need to know about Venus is that it rotates the opposite way. So it rotates clockwise while all of the other planets rotate counterclockwise. Earth is called the Goldilocks planet because it's perfect for sustaining life. And then we get to Mars. Mars is our red planet. There's a lot of iron oxide in the soil. It also has the tallest volcano and mountains in our solar system. Again, it is dead and barren and there is no life on Mars. Into the outer four, our Jovian planet, starting with Jupiter. It's our largest planet. The last release from NASA stated that it has 79 moons. So there's a lot of different numbers out there, but that was the latest count. One of the largest ones is called Europa, and they're thinking that it could possibly sustain life. On Jupiter, there's a big red dot, which is it's a big storm. It's been there for over 400 years, and the storm itself is 2 times the size of the Earth. Saturn, we know, is known for its rings. It's made of different types of ice chunks, and it has a large moon called Titan. It has more than one, but that's the largest one. Uranus rotates on its side, and it was the first planet to be discovered with a telescope. And then Neptune is the furthest from the sun. We cannot see it from the Earth just because it is so far away, but it does appear to be blue due to the methane atmosphere. And so we remember the order of our planets by using an acronym, which is My Very Eager Mother Just Served Us Nachos. Or if you can remember Move Jason, that will help you remember as well. MV, Move, M-E-M, Jason, J-S-U-N, Move Jason. That will help you remember the order of the planets from the sun and outward. Okay, moving on, talking about Earth's tilt. We've talked about this already when we were talking about precession and nutation. But we know that the Earth is tilted on an axis of about 23.4 degrees. Perpendicular to the plane of the orbit, and the tilt of the axis causes us to have seasons. You do need to know when the solstices and the equinoxes are. We know the Earth revolves around the sun in an elliptical shape, and with the tilt of our Earth, we get our seasons. And so here are our seasons. Remember those words aphelion and perihelion. So this doesn't give us a good look, but we are furthest from the sun during our summer solstice in June and closest to the sun in December. Actually, remember that the sun is one of our focal points, and during December, we are closest to the sun, so the sun is more like here, not here. In December, it's closest, but we are tilted away from it, so we have winter. And in the summer, even though we are aphelion and furthest from the sun, we have summer. So make sure that you just write down when our the autumnal and vernal equinoxes are, and then our summer and winter solstices. Okay, moving on. If we look at the tilt of all of these planets, it says if tilt determines our seasons, then the planets that don't have much of a tilt would experience very little seasons. So there's 3 planets, if we take a look at them, that are going to experience very little seasonality because their tilt is very close to non-existent, pretty much straight up and down. So if you had to guess, it would be really easy to find that both Jupiter and Mercury, because their tilt is only 2 and 3 degrees, are going to experience very little seasonality. But also, if you look, remember, Venus is that retrograde planet. It is 177 degrees, and that is 180 is opposite of 0. So that is basically straight up and down as well. It would be a 3-degree difference. So Venus would also experience very little seasonality compared to the rest of our planets. So when we start talking about seasons and tides, moving into tides, tides are caused by the gravity from the moon. So the Earth is pulling on the moon, but the moon also pulls on the Earth. It just doesn't have as much gravity as the Earth does. But the gravity of the moon does affect us more than that of the sun when it comes to tides because the moon is so much closer. So remember that we talked about gravitational theory, that the further something away is, the weaker the gravity, the closer it is, the stronger the gravity, but also it was determined by mass. So obviously the sun has a huge mass, but it's also far away. So it does affect us, but because the moon is much closer to us, its gravity does affect our tides. So it affects our water, and we have tides. When the sun and the moon and the earth are lined up like they are in this picture here, that creates what's called a spring tide. Spring tides give us the highest high tides that we during the equinoxes when the sun, moon, and earth are perfectly lined up. And this is what I was talking to you about as well, that the sun does have an effect on our tides. It's more massive, so it has more gravity, but because it's so much further away, its impact is less. But we are going to see, so in this example, we see the sun, moon, and earth all lined up, and they're going to work together. That's why we get the highest high tides. But there's another tide called neap tides we'll talk about in a second, where the gravity from the sun and the gravity from the moon cancel each other out due to their positioning, and we get the lowest low tide. So let's look. That's what I just said. The sun's impact can add to or fight against the moon's. Okay, so when we're talking about tides in general, there are 2 low and 2 high tides that happen each day. They're about 6.5 hours apart. So you can see from this example here that every 6.5 hours we're going to have a low, high tides. So this is the neap tide. This is when the sun and the moon are going to fight against each other. So you can see the sun is up here and the moon is over here. When they are not lined up, but they are perpendicular to each other, we are going to have the lowest low tides because the gravity of the sun and the gravity of the moon are canceling each other out. And then in this example, you have your spring tides, and that is when our sun and moon and earth are lined up. So it doesn't matter where the moon is on this one, sun, earth, moon, this one, earth, moon, sun. It doesn't matter how they're lined up, but when they are in a nice straight line, that is when we get spring tides. Let me show you a quick video clip.
In this diagram, the earth will be a blue circle, the moon will be a white circle, the sun will be a yellow circle, and the ocean will be represented by this blue bandaroo. Now, let's just focus on the earth. This is our location on the earth as we spin around its axis. If tides did not exist, the sea would just be a sphere around the earth. However, the moon is the most influential component that affects the tides. When the moon is located on this side of the earth, it will pull the oceans toward it on both sides, leaving 2 humps of water on each side of the earth. This creates 2 different types of tides, low tide and high tide. Each turn is approximately 6.5 hours until there is a different type of tide. As the earth rotates, we will be seeing high tide here, low tide here, high tide here, and low tide here. The sun influences the tides as well. When the sun is placed here, it lowers the effect of the moon on the tides and begins to look more like this. Then, when the sun is in line with the moon, it moves the tides to create super high tides and super low tides because they are both pulling the water. This configuration of the earth, moon, and sun is known as the solar eclipse. Similar tides can be created when the sun is placed on the opposite side of the earth. When it is here, it has the same effect on the tides, extremely low tides and extremely high tides. This correlation of the sun, earth, and moon is also referred to as a lunar eclipse. So basically, the lunar eclipse and solar eclipse create spring tides. There are a lot of other factors that influence tides, but this is a very simplified version of how tides are created.
So your spring tides are going to give you the highest high tides and the lowest low tides. Where your neap tides, you're not going to have a big difference between the tides. Your high tide, low tide are going to be about the same during a neap tide because there's not gravity affecting it to make it bulge at the sides like we looked at in a minute ago. All right, let's continue on. Moving into fission and fusion, we talked about this a little bit with the sun. Fusion is where our sun's energy comes from. We talked about already that 4 hydrogen atoms fuse together to form 1 helium atom, and large amount of energies are released when this happens. The other type of nuclear energy is called fission, which is breaking an atom apart. Again, huge amounts of energy are released. Think atomic bomb, power plants, and nuclear reactors use fission to create energy. In the sun, fusion is how we get our energy. So the same thing, the process by which 2 or more low mass nuclei, like hydrogen, if you remember your periodic table from 8th grade, or if you've taken chemistry, hydrogen is the very first element. There's only 1 proton, 1 neutron. So those low mass nuclei of your hydrogen join together or fuse together to form another nucleus, which is called fusion. So 4 hydrogen atoms equals 1 helium atom. And again, large amounts of energy are produced. So in our sun, from the photosphere, energy leaves the sun as light, which takes 8.3 minutes to reach our Earth. So that means after the sun sets, we still have 8.3 minutes of light because it takes that long for light to reach us from the sun. The sun also creates other types of energy called the electromagnetic spectrum, which I am sure you are familiar with. We're going to talk about it in a second. And then the constant flow of these magnetic fields from the sun is called solar wind, which can be damaging to us, but our Earth has some protection in place. So here's the electromagnetic spectrum. So we are looking at low frequency. Whoops, and I didn't go in drawing mode. Let's go back up. Okay, so let's get in drawing mode. Okay, so these are low frequency waves. They are least harmful to us, which is super important for you to know. Least harmful. It would be really good for you to draw the spectrum in your notebook. So the longer waves are least harmful, while our shorter waves are most harmful. Sorry, I'm writing with my finger and it is messy. But stars or our sun produce all of these wavelengths in various quantities. In the middle here is our visible light. So that is how the electromagnetic spectrum works. The least harmful waves have the lowest frequency and the lowest energy type, while our most harmful waves have a high frequency, meaning there's a lot of these happening in a short period of time, and they have a lot of energy. Let's talk about those some more. Okay, so everything you just saw on that electromagnetic spectrum are forms of energy. Infrared, infra means before, so if it's infrared, it means it comes before the red color on the electromagnetic spectrum. And ultraviolet, ultra, that root word means after, so that means those types of waves are going to come after violet on the electromagnetic spectrum. This is what I was talking to you about a minute ago. Get back. Longer wavelength, lower frequency, least energetic, those are our radio waves. Shorter wavelengths, higher frequency, more energetic, those are the ones that are most harmful to us. And in the electromagnetic spectrum, all the way on the right, we saw gamma rays, but cosmic rays come after gamma rays. And so the solar rays are what's going to bring in cosmic rays. But again, we have our Earth protects us. We're going to talk about the magnetosphere in a second. Other things you need to know: red has the longest wavelength of the visible spectrum, meaning it's least energetic. When we're talking visible spectrum, we're talking about light and how light breaks down into the Roy G. Biv colors. So red is least energetic. Violet has the shortest wavelength, so it's going to be most energetic of our visible spectrum. And then when we talk about the extremes of the entire electromagnetic spectrum, radio waves are longest and safest. Gamma, X-rays, visible light, and radio waves are all types of electromagnetic waves that do come to our Earth. Okay, so as you can see here, if we look at the different types, if we start from lowest frequency radio waves up to the highest frequency, which is cosmic rays, we can see that radio waves, infrared, our visible light, and ultraviolet are the ones that are reaching our Earth. The ones that are very damaging to us, X-rays, cosmic rays, gamma rays, our Earth protects us from those. So Earth's atmosphere and the gases in the atmosphere, as well as our magnetosphere, protect us from the sun's harmful rays. And we're going to talk about the magnetosphere here in just a second. But this is what you need to know. This is what's reaching the Earth right here. Radio, infrared, our visible light, and then our near ultraviolet rays is what is reaching the Earth. The other harmful rays, the ones that are very energetic, are not getting to our Earth. So you may remember when we're talking about electromagnetic waves and how we get energy from the sun and how we get our light, that it travels through space as electromagnetic waves because they do not need matter to transfer. So there's three ways that we get heat transfer from the sun to the Earth. So conduction is direct transfer from items that are touching. Radiation is through thermal energy, and then convection. You've heard about convection currents. We have them in the water, we have them in the air. So warm air rises, cold air sinks. Warm water rises, cold water sinks, and then in our Earth as well when we're talking about magma with density. So the warmer something is, it rises, and then as it cools, it sinks. So that is happening as well. So how does that relate to our Earth? So solar heating by radiation of the Earth's surface is uneven because land heats faster than water. Because land heats faster than water, this causes air over the land to warm, expand, and rise over land, and then cool and sink over the cooler water surfaces, which is called convection currents. This differential heating is passed on to the air above by conduction, which causes air expansion and changes in pressure. And so what else do you need to know here when we're talking about heating? You need to know that water warms up warms up slowly and cools slowly. It contains, once it gets that warmth, it holds on to it. So it holds on to that energy. And then it lets it go off slowly. It's called a heat sink, meaning water takes a really long time to heat up and a really long time to cool down. And because of that, that causes the different uneven heating of our land surface. Land cools and heats fast, water cools and heats very slowly. That is very important for you to know. So what do we do with all of this energy coming in our different land surfaces heating? Well, we allow solar energy to be transferred into chemical energy through photosynthesis, and you guys already know this. It allows life on Earth possible. It allows food to be made. So what do plants need? They need water and carbon dioxide and sunlight. So here's carbon dioxide and water. We add sun's energy in the sunlight. And the plants have these handy dandy little organelles called chlorophyll, and with carbon dioxide, water, and sun's energy, they are able to create, their product is sugar, that C6H12O6 is called glucose, and oxygen, which we need to live. So plants use energy from the sun, which is the energy transfer is from nuclear energy. Remember, fusion is happening. And that gives us radiant energy, which is light. The light travels through electromagnetic waves to our Earth and allows our plants to make food or glucose for the plant, which is called chemical energy. So we go from nuclear to radiant to chemical. Photosynthesis transforms a very small amount of the solar energy coming into our Earth into chemical energy. And if something happened and we had a decrease in energy from the sun, that would result in a decrease in the rate of photosynthesis, which would have a harmful effect to all life on Earth. And this is the last thing we need to talk about, which is the Earth's magnetic field. So because of inside of our Earth, the core so the inner core and the outer core, they rotate opposite ways. And because they rotate opposite ways, and because the core of our Earth is made of iron, we get this magnetic field happening. And so you can see what's happening over here. We have this magnetic field that comes out, and then we have like this tail region in the back. We have this awesome magnetic field. The shape is compressed closest to the sun and has a tail-like tadpole on the opposite side due to solar winds. So here's the solar winds coming in. Here's that tadpole shape at the back that they were talking about, and this compression of our magnetic field here. But this protects us from the solar flares and from those we were just talking about the cosmic rays coming through. And so why is solar wind so bad? Well, it can cause blackouts, it causes cell phone disruption, it destroys satellites, GPS, TV, cell phone. So without our Earth's magnetic field, we would not be very happy without all of our electronic and being able to figure out where we are on Earth and where we're going. Let's talk this a little bit more. So this is the last thing we need to talk about. I already talked to you about the rotation of the inner and the outer core, which causes our magnetic field. It's called AC, which is alternating current, and it's exactly how our electricity works as well. But our magnetosphere protects the Earth by preventing those high-energy solar particles from reaching the Earth, that solar wind. But the really cool thing is that we get this awesome light show called the Aurora Borealis, which is created by the collision of particles from the sun with our atmosphere and our magnetosphere. And so I'm sure you guys have heard about that before. That is it for our astronomy unit. Please make sure you ask me questions if you're confused about anything.